Over the years there have been an innumerable number of books, TV shows, comics, in which characters are shrunk to microscopic sizes or enlarged to huge ones. Everything from Gulliver's Travel to Ant-Man, Honey, I Shrunk the Kids, Fantastic Voyage, lots of these things. And normally when someone in these movies is shrunk down very small, they can walk around and do all the normal things they do in their full size. But as we'll see, that's actually not very realistic. Physics is different at small scales. It's not that the laws of physics are different, it's just which law of physics becomes really important is different. Now, the first reason for this is the relative strength of two forces of nature, electricity and gravity. Now, you'd naively expect electricity to be much stronger than gravity. Let me explain why. Let's imagine we have two people, both weighing about 100 kilograms, so 100 kilograms each, separated by, I don't know, about a meter. Now let's look at the gravitational and the electromagnetic forces between them. Now the gravitational force is given by Newton's law of gravity. So force equals G times the mass of the first person times the mass of the second person, m1, m2, over the distance squared. Now G, this constant here, is the standard Newton's gravitational constant, 6.67 by 10 to the minus 11, which is roughly 10 to the minus 10. Mass is 10 to the 2 times 10 to the 2 over the distance, which is 1 squared. So that comes out as a whopping 10 to the minus 6 newtons. Whoa! So this is why you're not attracted to the person sitting next to you. Or maybe you are, but not gravitationally attracted to the person sitting next to you. It's very, very tiny. But now let's look at the electromagnetic force. And what we're going to assume is that both people have 1% too many electrons. So we'll put some negative charge all over them. Now, how many electrons is 1%? Well, how many electrons are there in a body? Electrons don't weigh very much, but generally speaking there's going to be one proton for every electron. And most of the mass in your body is protons, certainly within a factor of 2. So, I mean, there are neutrons in there, but the most common element in your body is hydrogen, which doesn't have a neutron, and it's going to make less than a factor of 2 difference. So how many protons in a body? Well, that's going to be roughly mass of the body divided by the mass of a proton, with some factors of 2 or so to allow for neutrons, which we're going to ignore. So that's about 10 to the 2. Mass for protons about 10 to the minus 27. So that comes out as about 10 to the 29 protons or electrons. Now each electron has a charge of 10 to the minus 19, actually 1.6 by 10 to the minus 19 coulombs. So the total charge is about 1%. Remember, we're assuming they've got 1% too many electrons of 10 to the 29 times 10 to the minus 19, which is going to come out as about 10 to the 8 coulombs. Okay, so if someone gives you 1% too many electrons, it's 10 to the 8 coulombs. That's a lot of charge. So now what's the electric force between you and your neighbour? This is given by Coulomb's law, so force equals constant 1 over 4 pi epsilon naught Q1 Q2 over r squared. So Q1 and Q2 is about 10 to the 8. So that comes out as about 10 to the 8 squared over 4 pi, which is roughly 10 times 8.9 times 10 to the minus 12 times 1 squared, which comes out as about 10 to the 26 newtons. Whoa. Okay, so gravitational force between two people, 10 to the minus 6 newtons. If they have 1% too much charge, which is not a very big percentage, electrostatic force between them 10 to the 26 neutrons. So you've got 32 orders of magnitude difference between the forces with only 1% of charge. I mean, this is enough force to rip the Earth in half. So, this is what I mean by saying you'd expect electromagnetic forces to be much stronger than gravity. And indeed they are at atomic scales. If you do the similar sort of calculation for the ratio of the electromagnetic force between an electron and a proton and the gravitational force, you get similar enormous ratios. However, in everyday life, electromagnetism is not that important, whereas gravity is very important. Why? Well, basically it's because electrons and protons are exquisitely well balanced. They are exactly the same numbers of positive and negative charges. And so that means when you're on a big enough scale, everything, the electrostatic forces cancel out, and even though you've got this incredibly strong force that's 32 orders of magnitude stronger than gravity, it cancels out so perfectly. And on the other hand, gravity don't have positive and negative charges. So gravity can't cancel out. It always adds up. And even though it's very, very weak compared to electrostatic forces, because it always adds up, because there are no negative masses to cancel out the positive masses, eventually when you get up to enough atoms and enough scale, gravity wins.